So in terms of an overview of my presentation, I'll talk a little bit about the principles of low temperature geothermal energy, some terminology and technology, so I'll quickly go through those, and some statistics, and some of the barriers to implementation of this technology here in Ontario. And this study in particular, talking about overcoming some of the technical barriers through some work at York University, TRCA's head office, and scale-up potential for the Greater Toronto Area. And lastly, step into some next steps. Geothermal has been around a long time. We think of it now because it's been in the papers. We've seen more and more implementation here in Ontario. The first heat pump was actually built back in 1856, and the current technology, or essentially the current technology, shell and tube, was developed back in the 20s. And essentially, you think of it as using electrical energy to transfer thermal energy from a source to a sink. So it either takes warm air from your house or your building, puts it outside in the summer, or it takes thermal energy from outside and moves it inside during the winter. And one of the key things here is it's most efficient when the temperature differences between source and sink are small. Excuse me. And things to think about, GTA ground temperatures are typically 8 to 12, while monthly GTA air temperatures range between -3 to 21 degrees. So you can see automatically or quickly here that the groundwater gives us some nice stable temperatures to work from that can be very thermally efficient. I'm very quickly talk about some of the terminology here. Seasonal energy efficiency ratio gives an idea of the cooling efficiency of a heat pump or air conditioner. Coefficient of performance, that's the ratio of heat transferred to how much energy you put into the heat pump. A closed loop system, it's a subsurface system that essentially transfers thermal energy using a liquid through either vertical or horizontal piping. Open loop involves the extraction of water to and from an aquifer. So essentially you take it from the aquifer and then you put it back after putting it through the heat exchanger. And thermal storage specifically involves storing that thermal energy. As you can appreciate, after the groundwater goes through a heat exchanger, it comes out a different temperature than what it came in at. And thermal storage uses that to create a cool area in the aquifer and a warm area in a separate spot. So then you have warmer water to use in the winter and cooler water to use in the summer. That's what it looks like in pictorial form with cooling mode, heating mode of an open loop system in this case. And you can see the thermal energy storage here on the right, lower right, with the warmer wells and then two cooler wells over on the left. And so for a closed loop system, they can either be horizontal in a trench, vertical, and single array, multiple arrays, and they can have thermal storage as well. With open loop system, you need a minimum of 2 wells, one for withdrawal and one for injection. And if you're going to do thermal storage, you have to have valves and electronics to control the flow direction. I'll just quickly throw up some statistics. Your conventional HVAC, your COP is less than 1 and SEER of 10 to 14. Then look at the heat pumps, COP of 3 to 4 for ground source or open loop, SEERs of anywhere from 14 to 27. And the coefficient of performance at 8 degrees Celsius air temperature is about 2 to 5, and at -8, it's 1 to 4. So that's where it comes in that if we are able to use groundwater at a more regulated or a regular and predictable temperature, will have more efficiency for the heat pump. Some of the benefits, again, 35–40% reduction in greenhouse gas emissions because of the efficiencies of these systems. And if you're wondering why they're so efficient, it's because they're essentially moving the energy, the thermal energy. They're not creating it as you would in a furnace or creating coolness through an air conditioner. And we can see a potential reduction of space heating requirements from NRCan data from 61 megatons to potentially 25 to 30. And if we decarbonize our electrical grid, the potential is to get to zero emissions. And they also save us money. Over the lifetime of a furnace or heat pump, gas furnace versus a gas furnace save about 70,000, or cost about 70,000. Air source heat pump about 65, and a ground source heat pump at 45,000. So significant savings potentially over the long term. And you can have even further reductions if that energy is used to preheat your hot water. So if this is so great, where are the barriers? Well, one of the first, especially for open loop, is what I'll call the perceived risk of aquifer contamination. Because you're taking water out of an aquifer and putting it back, if anything happens to that water in between, obviously there's the potential to contaminate the aquifer. Capital costs. Deep boreholes and wells are certainly not cheap. They're capital intensive, require that money up front. And as soon as you involve thermal storage, now you've got more pumps, more valves, more controls. And there's also the risk with all these technologies, subsurface technologies, with interference with existing buried services. As you are likely aware, more and more, all our new developments have a lot of buried services, and more buried services are being installed every day. So we have to be careful not to poke holes through fiber optic cables, obviously electrical cables, and all the other subsurface infrastructure that's present in our communities. And hydrogeologic uncertainty is a big part of the risk. And people are willing to put up some capital if there's a certain return. But with groundwater, as most of us know and are aware, there's a lot of uncertainty. We've heard some of that earlier today. An example from our new head office, not a big piece of real estate. We have 2 wells there that make more than 500 liters a minute. We have 1 well that makes less than 225, if that. And it's on the same property, same aquifer, same depth. So this uncertainty is not something industry and homeowners are not willing to tolerate, obviously, especially when they're putting up those capital costs at the beginning. And lastly, we have regulatory approvals to overcome with environmental compliance approvals here in Ontario, and also a permit to take water when you're taking water out of the aquifer in an open loop system. So how do we solve some of these problems? The idea is to reduce uncertainty by utilizing some of the regional hydrogeologic databases you've heard about through this conference this year and other years. Geophysical screening is a great approach. And again, we've seen some examples of that. And producing screening maps that people can use to review the area that they're looking at and see what might be possible in their area. And in terms of installations, of course, contractor certifications will obviously help in ensuring that we have quality installations that don't impact our groundwater systems. And the other 2 points, installing systems as part of the development process, getting them in early as opposed to waiting until everything else is in, can help avoid some of the other infrastructure interferences that we've seen. And standardized materials and construction methods can hopefully bring the costs down over time. So what do we do here at York University? This was part of a partnership that we were involved in. Did some surface geophysics, a great way to look for buried valleys that might contain good aquifers for thermal energy storage and identify areas of potential yield before you go to the expense of putting in a well. In this case, we weren't too successful, but the idea is that it was a lot less involvement than trying to poke holes all around campus, trying to find a valley and doing it in the dark. Some of the interpretation, we did find a bit of a valley. Wasn't necessarily large enough to service the university and meet their high needs, but this is something that could be used perhaps for a single building or a couple of buildings on the campus. And again, this is non-intrusive. You can cover a lot of ground in a hurry and then drill targeted boreholes exactly where they're needed. We also use downhole geophysics, and this was from a well at head office. And it can help refine some of the information that you have from drilling. You don't always get 100% recovery. So going back with geophysics, we can look at sediment properties, even porosity and permeability can be estimated now with some of the new tools. And every year it seems the tools get better and better and smaller, and they're able to put a lot of their tools down a 2.5-inch well now, which opens it up to a lot of the wells installed by the consulting community. So what did we learn at the local scale? We need, for thermal energy storage, we need a consistent productive aquifer. We recognize that borehole thermal energy storage is best in rock or saturated sediments as you get better thermal conductance. And we also learned that bedrock valleys are poorly understood in the GTA, despite all the holes that we've been poking in the ground over the years. For instance, at our head office, we didn't think the valley was there at first, but we found that actually we were on the very edge of a significant bedrock valley. We also recognize that uncertainty costs time and money as we're trying to decide where to put holes. Can we find enough water for our new head office, as an example? And we recognize that in the face of this uncertainty, property owners will revert to proven technologies. So the idea was to kind of scale up some of this knowledge to the Greater Toronto area. We recognize some of the process goals that we wanted to have. Sensitivity, so your screening tool must be sensitive to the hydrogeologic conditions. Specificity, so that you can identify where the technology actually has a good probability of success. And that comes into positive and negative predictive values as well. You want to be sure if you say, yes, this is an area that it could be feasible, that there's a reasonable expectation that you'll meet the needs of the property in question. Or in the case of negative predictive values, to say, no, this is not an area that aquifer thermal energy storage or borehole thermal energy storage will be appropriate. So we looked at various parameters, we mapped some results, did some subjective evaluation, and then narrowed the parameters to fit the goals to produce, I'll call them the final maps. We're still not 100% done this, but the idea was to take these various options we had from the regional mapping and look at which ones provided the best answers to our questions. And we had examples like driller recommended pumping rates, estimated hydraulic conductivity, sand and gravel thickness, and total aquifer thickness. And we also had energy screening, because it's not enough just to understand the nature of the ground, but also identify areas where high yield systems would likely or could likely be utilized, because these are the systems that'll save the most and provide the most volume and energy needs to justify an open loop system. We use land use as a surrogate because those data are readily available and they're consistent at the regional scale. So in the end, we used all the existing hydrogeological data we could get our hands on, subways, sewer studies, deep foundations, to improve our understanding of the hydrogeology. We overlaid the geology with areas of anticipated high density development, commercial, industrial, large scale residential. And we recognize that other areas may be better suited to borehole thermal energy storage or closed loop systems. And that's something that could be looked at in a future study. And without further ado, here's our preliminary screening map. Doesn't look very pretty at this point. We may be looking at changing some of the colors around to make it a bit more aesthetically pleasing. But essentially the darker areas are areas where we have the best aquifer potential. And the brighter areas in green here are areas where we have mixed commercial, entertainment, and high density residential in yellow that have the best, red and commercial that have the best chance for larger scale systems. The next steps for this, we hope to improve both our geologic and hydrogeologic models, do some more surface and downhole geophysics to expand our knowledge of those and how effective they are. And we want to test some of the screening process with hopefully some municipally led projects where there's a little more tolerance for refining the geologic system, I'll call it. And then we also want to do some reviews of other large scale geothermal systems in the GTA. We know there have been some installed. Look at some of the successes, compare against the screening maps to see how, if there's a good match against that, and then perhaps we'll have to update our mapping as required. And along with that, we'll be monitoring our new head office geothermal system, which is an open loop system.